Okay, let's start with this question. What do all of these molecules have in common? Um, if you look at them, right, what we see is that in this case the ratio is 3 to 6 to 3 carbons, hydrogens to oxygens. Here it's 5 to 10 to 5. Here it's 2 to 4 to 2, 6 to 12 to 6. What all of these have in common is what's called an empirical formula. The empirical formula of a compound is the lowest whole number ratio of atoms. Sorry, I should say of elements, but atoms works too. In a molecule. Okay, so all of these have the same empirical formula, and their empirical formula is that lowest whole number ratio. So it's probably simplest to look at the smallest numbers here, C2H4O2. And then we can see pretty clearly that our empirical formula is CH2O, which, interesting, is actually the root of why all of these types of compounds are called carbohydrates. So you get a carbon and then a water. Now that being said, in these molecules, the water does not exist as a molecule, but that's the root of the name of this. Carbon and water, carbohydrate. Okay, so let's get some definitions out of the way. I just mentioned what an empirical formula is on the previous page, but let's also talk about what a molecular formula is. A molecular formula is going to be the actual ratio of elements or atoms in a molecule. So going back to our previous example, if C6H12O6, which you guys might remember as glucose, is the actual composition of the molecule, that's its molecular formula, even though it shares an empirical formula with a bunch of other compounds. And what this means is that there's actually 6 carbons in some way, shape, or form bonded to these 12 hydrogens and to these 6 oxygens. Unlike in an ionic compound, where we've used the word formula unit to describe what's going on. So a formula unit, remember, is the lowest whole number ratio. And that language should sound familiar from empirical formula. But formula unit is the lowest whole number ratio of ions that forms a neutral compound. Remember, the reason we don't talk about ionic compounds in terms of molecules is because unlike molecules in which, for example, we might have this ammonia molecule interacting with a neighboring ammonia molecule, which I'm dropping, interacting with a neighboring ammonia molecule through kind of intermolecular forces. In ionic compounds, we would have nothing special about the interaction between this sodium and this chloride as opposed to, oh gosh, this model is really screwed up, as opposed to this sodium and this chloride over here. So an ionic compound is completely held together by ionic bonds, so it's inappropriate to talk about it in terms of molecules. Molecular formula, we are talking about kind of discrete molecules that are interacting with their neighbors in unique ways. Okay, so that gets all the definitions out of the way. Let's look at one type of problem we'll be doing, which is just like looking at things and figuring out the empirical formula. In this case, this is also a nomenclature test. So copper 2 hydroxide, remember the 2 refers to the charge on the metal. And remember, metals are always positive. Okay, so here we have copper 2 plus combining with hydroxide, which you'd need to memorize as OH minus. That means we need 2 hydroxide ions for every 1 copper. Okay, and so here the empirical form, I've determined what the formula of copper 2 hydroxide is. And now looking, I see that the empirical formula and the formula unit of this are exactly the same because I can't reduce this ratio anymore. I've got 1 copper for every 2 oxygens for every 2 hydrogens. This is often the case, actually almost exclusively the case, in terms of ionic compounds. For ionic compounds, their formula unit is 99.9% of the time the same as their empirical formula. So let's look at a covalent compound. I know this one's covalent because it has nitrogen and hydrogen in it, and those two things are both nonmetals, so it's easy to classify that using that kind of simple tool. In this case, I've got 2 nitrogens for every 4 hydrogens. This is also commonly known as hydrazine. And I look at this ratio and I say, well, this is the molecular formula, okay, because the name will always talk about the molecular formula, will always describe the molecular formula. The empirical formula is going to be the lowest whole number ratio of those two things, so NH2. Last but not least, we've got C4H10. Again, in this case, we're going to divide both things by 2 to get the lowest whole number ratio, C2H5. Okay. Well, why do we care about all of this? Because this is actually all part of how we characterize things to begin with, right? So if we have some sample and we don't know what it is, we might use something called combustion analysis to figure out what elements are present, and also to figure out what ratio or how much of each element we have. Okay, we might use something like this. Now this particular version would only allow us to figure out something that has only carbon and hydrogen in it. Well, actually, you could have one other thing in it, but we're not going to go into that. So you could have, for example, nitrogen in it as well and figure out how many nitrogen molecules there were. But essentially, every time we do a combustion or elemental analysis, the information we get out is about what elements are present. So in this case, we'd find out if hydrogen was present and my sample reacted with oxygen, I would find the mass of this H2O absorber increasing as the sample flowed through. Why? Because the whatever CXHY is being combusted here, combustion is always reaction with oxygen to form H2O and CO2. So whatever's being combusted here, the H2O will be absorbed here, and whatever the change in mass of this particular component is will relate to how much hydrogen was in the original sample. Similarly, however much carbon dioxide, however much the mass of this thing changes over here, will relate to how much carbon was in that original sample. Because if you look at this reaction, the only place that hydrogen is coming from in this particular reaction is our sample. The only place carbon is coming from in this particular reaction is our sample. And so we can use these relationships to figure out what elements are present, what ratio, and how much of each element we have. The type of data you get out, you get masses of each element, or you might get the percent of each element in your original sample, or if you're really lucky, you might get the moles of each element. Okay, and that's generally how a problem dealing with empirical formulas will start. This type of analysis will only give you the data to find an empirical formula, the ratio of things, rather than a molecular formula, which is the actual, molecular composition. So this is the type of problem that you're going to end up seeing. If you did a combustion analysis on nicotine, you would find that a 74% carbon, it's 8.65% hydrogen, and a 17.4% nitrogen. And if I find the empirical formula from this data, this is how I'd go about it. first, if you're starting with percents, that's actually the hardest way to start, which is why I wanted to do this problem rather than starting with masses. I'm always going to set it up like this. Okay. First things first, when you have percents, you need to get a mass amount. Okay, and that mass amount you can get in any way you want. You can pretend you have a 1 gram sample, you can pretend you have a 5 gram sample. I think it's easiest to pretend you have a 100 gram sample. Why? Because when you do that, that means you actually have 74.0 grams of carbon, you've got 8.65 grams of hydrogen, and you've got 17.4 grams of nitrogen. Once you have pretended that, you need to convert everything to moles because a chemical formula, right, so our nicotine has, the following general formula. Sorry, that should be an N with a Z. These values are mole relationships, okay, number relationships. Yeah, actually, number is better than mole. These values are number relationships, not mass relationships. So you need to have these values in moles. So I'm going to divide carbon by its molar mass. I'm going to divide hydrogen by its molar mass. And I'm going to divide nitrogen by its molar mass. Sorry, 14.01 grams. 1 mole. Okay. And when I do that, I get values. I get 6.16 moles. I get 8.56 moles, and I get 1.24 moles. Again, it's probably pretty important to just kind of keep track of what you're talking about in each case. Okay. Once I have moles, I look at, what I think of as a chemical formula with these integer values as x, y, and z, and I realize that these mole values that I have are not integer values. The way that you make these integer values is by dividing by the smallest number of moles. Okay, in this case that's nitrogen. I've only got 1.24 moles of nitrogen, and I've got many more moles of hydrogen and carbon. The reason you divide by the smallest number of moles is to try to get integer values. So obviously the first thing you see is that the number of moles of nitrogen now would be 1. Okay, so we got 1 mole of nitrogen for every, plug that in, 6.9 moles of hydrogen. When you get a value like 6.9, you can approximate that pretty easily to 7 in an empirical formula problem. Don't round here. Do round at the end here, though, once you're making these whole number ratios. And up here with carbon, I see 4.96, which approximates very well to 5. So I'm still not done. I've got the ratio of nitrogen to hydrogen to carbon in my compound, nicotine, but I need to write it as an empirical formula, which looks like this. So this is my empirical formula of nicotine. The last type of thing you might be asked to do is to figure out the molecular formula of nicotine if the molar mass is 162 grams per mole. You're always going to need to be provided the molar mass or some information to figure out what the molecular formula is from the empirical formula. So if I know that this is my empirical formula, the first thing I want to do is I want to find the mass of the empirical unit. Okay, and the mass of the empirical unit is 5 times 12.01 plus 7 times 1.01 plus 14.01. And so the mass of the empirical unit is about 81 grams per mole. And I want to figure out what its relationship, the empirical formula's relationship, is to the molar mass of nicotine. I essentially want to see how many of these units go into the overall molecule. So I'm going to do that by dividing the molar mass of the nicotine, right, the whole, by this piece that I know exists in the whole. And of course I see that this ends up being 2. Okay, what does that mean? That means that I've got 2 pieces like this in my overall molecule of nicotine. So all I have to do is I have to multiply each of the subscripts by 2 to get my molecular formula, which for nicotine is C10H14N2.